Nothing too bad, right? And again, we know we're doing it 3 times, so we have 3 equivalents, and we have 3 locations where we can attack. Both those things are important, because if we only had 2 equivalents, we'd only attack 2 of the alcohols. And if we only had 2 alcohols and 3 equivalents, that extra equivalent means nothing to us. So make sure you keep an eye on the number of alcohols you have and the number of PCC equivalents you have. Because I have seen him change the number up a little bit. You'll have this, like maybe this exact same structure, but then you'll have PCC, but only 1 equivalent. It's only going to attack 1 of the alcohols at that point, so you would not draw 3 of these as aldehydes. You'd only draw 1 of them. So make sure you guys pay careful attention to that. Odds are he probably won't troll you like that, but in case he does, just keep an eye on the number of each thing that you've got. Any questions on this guy? This is pretty standard PCC. Like I said, I've seen this exact one several times on finals, on quizzes, and on midterms. So this guy doesn't really seem to go away. All right, ready to go on to the next page? All right, let's do it. Let's look at the next page. What do we got here? Well, it wouldn't be chemistry without the D. Gotta have it. There it is. We're adding some nice deuterium to this. Quote-unquote elemental deuterium, I guess. And we're using palladium and carbon as a catalyst. Now, this one is a slightly modified version of H2 with PDC. But they follow the exact same mechanism. So I'm going to put this over here as a little side note in case you guys haven't seen a whole lot of these. If you got H2 or D2, and you're using palladium / carbon, you're turning an alkene into an alkane. And how you do this is you're basically ruining the pi system and attaching 2 hydrogens. So just like we saw with the 2 bromines, the only difference is the 2 hydrogens or 2 deuterium molecules are going to be cis with respect to each other because they can both attach from the exact same side of the structure. So we can have, like I said, either that or we can have the deuterium. Because again, what is deuterium at the end of the day? Yeah, but it's just a heavy hydrogen, so it's going to behave the exact same way. He just throws that in there just to throw you guys off. And also to sneak the D into the final. Because why not? So all we're doing to this structure is returning it into an alkane. And we have 2 equivalents, and we have 2 alkenes here we need to convert. So we just redraw the chair as best you can. Like that's probably going to be the toughest part of this, is actually redrawing the chair. So let me just redraw. Not bad, not bad. Not bad for almost 4 years of OChem. Not bad. And since this bridge is pointing up into the air, we're going to rather have the 2 deuterium molecules pointing down for us. And also, we've already technically got a hydrogen here sitting out here in the equatorial position. So we're not going to be able to really shove those out of the way. So we're going to attach from down below in the axial position. So we just draw the 4 axial positions, and they're all deuterium. So we just draw the D over and over again and fill up the 4 possible slots we've got. And that's it. That's all there is to it. So all we did was add deuterium to both sides of the structure. Good question here. So will we have to draw the deuterium in the axial position? For this particular example, yes. We will have to because the hydrogens are already assumed to be equatorial. And because even though deuterium is heavier than hydrogen, it's not going to be enough to push that hydrogen out of its orientation. We would need something larger in order to do so. Yep, biggest reason why we can't attach up top and move it is mostly because of this bridge structure. That's providing some steric hindrance, but the biggest reason is because of these hydrogens already occupying the equatorial positions. So it'll be a lot easier for the deuterium to attach from down below as opposed to up top. So basically everything is telling us deuterium must attach from down below. Good questions though, good questions. Any other questions on this guy? Anything else here? Like I said, You see an alkene adding H2 and palladium, you're hydrolyzing it. You're just tossing hydrogens at it until it is basically single bonded at that point.
How do we know the hydrogen is going to start off equatorial?
So over here, how do we know that the hydrogen is going to start off equatorial? So when it comes to double bonds sitting in ring structures, that's where things get really, really, really tricky. Because there's no stereocenter here, we technically assume that this guy is pointing sort of up, so to speak. It's kind of weird to kind of see from this particular angle. So we assume the hydrogen points out directly from it. Another way to look at it is it has to basically be parallel to the bond that's opposite from it. So remember our nice chair conformation drawing 101. This guy has to be parallel to this guy has to be parallel to this guy. That's why we're able to assume they're going to be in the equatorial positions, so to speak. And even then, this isn't even considered equatorial because there is no axial equivalent. But they're basically fanning outward, so not really pointing up or down. They're kind of just sticking out here. But once you add deuterium to this, you now have an axial position that can now be occupied by deuterium. And you do it both times on each side. It's going to depend there. Good question. So when it comes to ring structures, do we always assume hydrogen is equatorial? It is going to depend on the ring structure, and it's going to depend on the reaction you're doing to it. Because sometimes the hydrogen may be axial, so it's hard to tell. It all depends on the ring you're starting out with. Any other question on this guy? Like I said, gotta have it. Deuterium and PDC. Something very, very common you guys are gonna see. Again, just to trip you guys up. Oh no! You've gotta be joking me! Well, you guys are gonna have fun with this guy. What is this? That's ozone. This is the reaction I despise with a passion. Ozonolysis. This reaction is mean from an arrow pushing perspective, which you guys don't have to know. But I wanted to master it, so I learned the arrow pushing for it. I hate it with a passion. But I'm going to show you guys how to conquer ozonolysis. And a lot of students like ozonolysis because of how simple the products become. But ozonolysis is a very, very good way to break apart carbon-carbon double bonds. So to make life short, sweet, and simple, if you have a carbon-carbon double bond and you're introducing ozone to this along with some sulfur solvent that comes in afterward to kind of finalize the reaction, you're basically splitting the carbon-carbon double bond and replacing both ends with oxygens. So you've turned your structure into either a pair of ketones or a pair of aldehydes. So that's pretty much all there is to it for ozonolysis. Like I said, the products are very easy to arrive at, but the arrow pushing is a nightmare. It is a train wreck. I still have nightmares about this reaction. I hate it. So all we're doing to this guy is we're splitting these double bonds right here. Again, we have excess. So if we have excess ozonolysis, we're going to attack every single alkene that's in our structure. So we break the carbon-carbon double bonds apart, and we replace them with oxygens. But now here things get tricky, because splitting these bonds actually splits the carbon-carbon bond apart. So those carbons are going to separate. Now if we split this, this isn't really going to change much because these guys are all still connected together. However, when you split this one, you've now split the entire molecule in half. So in his fun answer key, he's only drawn one of those equivalents, because you guys probably counted the carbons out and saw that we were missing some. The reason why is because we split this bond right here and split this into two separate products that are going to be identical. So I'm only going to draw one of them because we don't need to draw both. So starting from this carbon forward, we've got one carbon here, so 1, 2, 3, 4, 5, 6, 7. So it's a 7-carbon chain that's got a carbonyl here, and carbonyl here. So we have basically one on each end. So let's draw ba-doop, 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 ba-doop. And yeah, so 1, 2, 3, 4, 5, 6, 7. So we got 7 carbons. You guys see where I got that from? I'll number them for you if you guys need. Here's 1, here's 2, here's 3, here's 4, here's 5, here's 6, here's 7. Makes sense though, right? like I said, I'm only drawing this half of the structure because when we split this bond right here, we split up into two identical ring structures. So we split this guy up, and now when we split this bond, that's going to make the structure linear at that point, because now we've opened up that ring structure. So now the only real challenge now is placing the double bonded oxygens in the correct place. So if I start off numbering, let's say this is the 1 carbon, we got a carbon-carbon double bond oxygen right there. So I'm just going to put 1 right there. Boom. And again, to make the molecule symmetrical, I will put the imaginary hydrogen there, because again, it looks weird without a hydrogen sitting there. But okay, so this is at our 1 carbon, so to speak. And if I count it out this way, here's 2, here's 3, here's 4, here's 5, here's 6, here's 7. We should have another carbon-oxygen double bond sitting out here at the 7 carbon. And again, I will put the imaginary hydrogen there so we look all nice and symmetrical, all nice and neat. And now we have another one that's sitting out here at the 3 carbon when we split the molecule in half. So we go to number 3 and draw a double bond there. Now I've had some students ask me, okay, do we have to show the entire structure all linear and broken apart like that? And the answer is not necessarily. If you're good at redrawing the exact same structure you started with, you're technically allowed to just sandwich the double bond oxygens in there like such in your product. And Wagner has been okay with this because he understands you know what's going on here. So you could draw either one. You could break the structure up and draw out the linear form of it, or you can just stuff the double bond oxygens in there and not have them separated. Because again, it's the exact same structure, it just hasn't been unfolded yet. But yes, that is ozonolysis in a very, very nice and compact nutshell. All you're doing is splitting apart alkenes to create carbonyls. That's your goal there. And like I said, the big dead giveaway is that you're adding ozone, and then like I said, some sulfur derivative to then split apart those carbonyls. Mm-hmm.
So on the exam, we only have to draw one of them, or do we put like times 2?
Yes. So for the exam, you would only have to draw one of these equivalents, because again, once you split this, you end up with 2 linear structures that are identical. And as you mentioned, you can also put a times 2 there if you want to make it more accurate. But either answer would be valid. You can draw one structure times 2, or just draw the one structure by itself. Hmm?
Can we number the carbon ring to the right? What if we number it to the right? You see how we go like 1 and to the left, and we count it to the right?
So what if we numbered it the other direction?
Yeah.
So if we numbered it the other direction, so if we said this was 1 all the way to 7, then we would just have the carbon-oxygen double bond at the 1, 2, 3, so it would be at 1, 2, 3, just be on this side of the structure. So again, it all depends on how you number it. It'll be near one of the 2 ends. Mm-hmm. I only put the hydrogens here. It's a good question. So why do I put the hydrogens there? I just put them there just for the sake of symmetry. In reality, you could leave your answer just like this, and it's perfectly valid. But that poor aldehyde looks kind of, I don't know, it looks naked without that hydrogen kind of sitting there. So we tend to just draw it on there. And for the sake of the graders, if they don't see you draw that proton there, they may very well mark you wrong for that. We've seen that on midterm 2, we've seen it on midterm 1, so when in doubt, try to make it all symmetrical and try to put that proton there. But again, that answer would be valid even without the protons there. So it's just a matter of saving you a regrade form, I guess, and some time. But good questions all around. Any other questions on ozonolysis? No, you will not need to know the arrow pushing for this. And even if you did have to know this, it would hurt me to show you because that's just mean. It's a mean reaction and mean to draw. So just know that if you got ozonolysis going down, you're turning an alkene into a pair of carbonyls. Any other questions on this guy? Any questions on the nightmare that is? Not too bad, right? Not too bad, not too bad. All right, let's look at the next guy. Ooh, what do you know? We got an alkene, we have diatomic bromine, but now he's got a friend accompanying him. This is going to change our reaction significantly from what we saw on the second page. Here we had just bromine just sitting here by itself.